Hey everybody, Dr. A here, and in this video we're going to be exploring another example of axial loads. So given to us, we're being told to draw the axial load diagram. And here we're given a figure. We're given an axially loaded bar that has a fixed connection over at A, and we're given a little X coordinate right here. This indicates to us that our origin is at point A and things pointing to the right are positive, okay? Now, at 4 meters, we have a 3 kilonewton load applied that's pointing to the left. And then at 8 meters, which is the end of the beam, or the end of the member, I should say, we have another load that's 2 kilonewtons pointing to the right, okay? And we're being asked to draw the axial load diagram. So let's write solution here. The first thing we're going to do anytime we want to draw an axial load diagram, I'm going to say first, solve for externals, okay? Now, remember, for an axially loaded system, our applicable equilibrium equations is sum of the forces along the longitudinal axis equals 0. In this case, we're going to say sum of the forces in the x direction equals 0. So if I draw a free body diagram of this system, let me draw that a little bit better. Not my most beautiful artwork. Okay, so here at the left side where point A is, we're going to have an AX, all right? And then at 4 meters, we have that 3 kilonewtons, and then all the way at the end, we have the 2 kilonewtons. And then we're going to go ahead and draw those dimension lines there. 4 meters, 4 meters. So here I'm going to say sum of the forces in the x direction equals 0. And I'm going to say positive AX minus 3 kilonewtons plus 2 kilonewtons equals 0. And then I'm going to do some rearranging, and I'm going to get AX is equal to 1 kilonewton pointing to the right. Okay? Now, how do I know that? Well, again, I'm just looking at this free body diagram, and I assumed AX was pointing to the right, so that's why it shows up as a positive AX in the equilibrium equation. 3 kilonewtons is pointing to the left, hence the negative 3 kilonewtons. 2 kilonewtons pointing to the right, hence the positive 2 kilonewtons. Do some rearranging, and AX comes out to be a positive 1 kilonewton, which means it is in fact pointing in the direction that we assumed it to be in that free body diagram. Now we're ready to draw the axial force diagram. So if you remember, we're going to set up a set of axes. The vertical axis is going to be force, and the horizontal axis is going to be an x location. And what are our units? Well, the force units are kilonewtons, and the x units are in meters, okay? So what we're going to do here is we're going to put a sign convention with that force, okay? So up here on this axis, I'm going to say things pointing to the right are positive. So here's what we do. We're plotting the variation of axial force along the length of this member. And we're going to move from left to right. So the first thing we encounter at the left side of the member is AX, and AX is pointing to the right, okay? That means that we're going to from 0, we're going to pop up by 1 kilonewton, okay? So what is that 1? That 1 is AX. AX was pointing to the right, and we said things pointing to the right are positive, so we move up the F-axis by 1, okay? Now we got to ask ourselves, what's happening between x equals 0 and x equals 4? Well, nothing. Nothing is changing between x equals 0 and x equals 4, which means that our diagram is going to stay constant until we get to x equals 4. Now, what happens when we get to x equals 4? We encounter 3 kilonewtons pointing to the left. So watch what I'm going to say here. I'm going to say the change in force at x equals 4 meters is going to be negative 3 kilonewtons, okay? Think about that. The change in axial force when I get to x equals 4 meters, this spot right here is going to be 3 kilonewtons pointing to the left, which in our case, left indicates negative. So what does that mean? That means that we're going to drop down all the way to what? What do you think we're going to drop down to? Are we going to drop down to -3? No, we're going to drop down actually to -2. Now, why is that? Well, we were at +1 and we encountered a delta F of -3, which means that from +1, we say -3, and that's going to take us down to -2. So it's that drop downwards. Now, what happens between x equals 4 and x equals 8 meters? Well, nothing. There's nothing in between there, which means that our plot stays constant. Okay? And then what happens finally when we get to the end of the member here? We encounter 2 kilonewtons pointing to the right. Well, that's going to do what? That's going to bring us back up to 0 here, okay? And the reason is because this distance right here, this is another delta F, and this is positive 2 kilonewtons, positive because it's pointing to the right here. So it's going to pop us back up to 0. And from there, we're pretty much done. Some people like to shade these in. That's what I like to do, just to throw some hatching in there. And this is our axial force or axial load diagram. Sometimes you might hear this called a normal force diagram. So if you ever hear normal force diagram, it's still this. It's just a different name for axial force diagram. So if you found this video helpful, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.